All right, now we're going to jump to the continuous case. As I said, the continuous case is a little bit more tricky, is a little bit more math involved in this. We're just going to touch upon the continuous case this week. But if you have any continuous mathematical function, if that function integrates to 1, that just means if the area under that curve is 1, then it is, by default, a probability function. The probabilities associated with a continuous probability function are just, again, areas under the curve, just integrals. And probabilities are going to be given for a range of values rather than any particular value. So in the discrete case, we talked about the probability that exactly 1 occurs, or the probability that exactly 9 occurs. With the continuous case, there are no particular, there's an infinite number of possible particular values. So we're always talking about the probabilities of ranges of values, like what's the probability that it will fall between 1 and 2. So let me just give you an example to make this clear. So a very simple but important probability function is the exponential distribution. And let me just write up what that function is. So the exponential distribution is e raised to negative x. We call that the exponential distribution in probability. And that function is just a mathematical function where the area under the curve is 1. And we can kind of just draw a picture of that function to see that. You can't have negative values. So it starts at 1 and it kind of goes down towards the x-axis like that. Now, if I just told you that the area under that curve is 1, you'd probably say that sounds reasonable, right? If you were to calculate the area under the curve here, it starts at 1 and it goes down towards the x value. It seems reasonable that that area might be 1. So if you want to just believe me, that's fine. I can also show you the integral for those who are interested. Again, this is optional, but we could take the integral over all possible values of this function. So you can have any value from, x can be anything from 0 to infinity. If we take the integral of e raised to negative x, we integrate it over from 0 to infinity, we get a value of 1. Again, that integral is just there for those of you who want it, but that just proves that the area under that curve is 1, therefore it's a probability function. So here's the same function just drawn out. We call this the e raised to negative x. We call that function a probability density function. It's analogous to a probability mass function, that little table where I wrote out if x is this, the probability of x is that for the discrete case. But really, the probability density function, it gives us this curve, but we can't really talk about the probability of any particular value off of this curve because there's an infinite number of possible just different values here. So we can't really assign probabilities to any particular value. We can only assign probabilities to a range of values. So we're always talking about a range of values. Because if you say, what's the probability of getting a value of 1? Well, do you mean 1? Or do you mean 1.0? Do you mean 1.023, right? So you're always really talking about a range of values. So that means that when we're talking about a range of values, we're actually talking about a cumulative distribution function rather than a probability mass function. But don't worry about that terminology. All that means is instead of looking at the original function, we're looking at the area under the curve. And again, areas under the curve happen to be calculated with integrals, but you can kind of look at this picture I'm showing here. So like if I asked what's the probability on an exponential function of being between 1 and 2, well, you could kind of just draw in that area and you could almost estimate it just from looking at the picture that that's around, a quarter of the area. Or you could do out the actual integral, which I'm showing on the bottom for those of you who want to see the integral done out. We could do the integral from 1 to 2, and we find out that precisely the area under the curve here is 23%. And here's an example of how this might be used in medicine. So let's say that we did a study and we found out that survival times after lung transplant roughly follow an exponential distribution, an exponential function. So people are dying after a lung transplant at a certain rate. If it follows an exponential function, then we can use that information, or approximately follows an exponential, to calculate the probabilities of survival in different time periods. So for example, the probability that a patient will die in the second year after surgery, somewhere between year 1, they will survive up through year 1, but die before year 2. That is, they will die between years 1 and 2. If we get the area under the curve, it's 23%. So their probability of dying in that interval is 23%. So it has very useful applications, the exponential function, in survival analysis. We'll talk about that in the very last week of the course. Another example of a useful continuous probability function is the uniform distribution. It's a very simple, nice little function, so it's easy to understand, so it's easy for illustrating some of these concepts. So the uniform distribution is just a distribution where x can only take on values between 0 and 1, and they all have equal probability, hence it's uniform. And you can see it just makes that function literally just makes a little box, a little square, and the area under the curve here, the area in that box has to be 1, right? The width is 1, the length is 1, so 1 times 1 is 1. You can also prove that the area under the curve is 1 by doing an integral here, should you choose. Of course, we don't really need that because everybody knows that the area of that box is just 1. So it's a very simple little distribution, and it's easy, even without knowing any calculus, to calculate areas under the curve here. So for example, if I said, what's the probability that x is between 1/4 and 1/2? Well, that's going to be 1/4. Or if I said, what's the probability that x is between 0 and 1/2? Well, that's going to be 50%. And this has real practical implications in medical research. So for example, when you're doing a randomized trial and you're randomizing patients, say you're randomizing half the patients to treatment and half the patients to control, the typical way that you would do that is to use a random number generator in a computer. And one of the random number generators available to you works by randomly generating a number between 0 and 1 with equal probabilities of all the numbers in between. In other words, it's based on a uniform distribution. Every subject has an equal probability of getting any number between 0 and 1, so you can arbitrarily say if the subject ends up with a number below 0.5, we're going to call them control. If the subject ends up with a number above 0.5, we're going to call them treatment. That will randomly assign people to treatment and control with 50-50 probability. And I had a case a couple years back where a student of mine had done a research project where she had randomly assigned people to a treatment group and a control group, and it actually literally flipped a coin, an actual coin, to decide where people were going, which group they were going to end up in. And the one of the reviewers of her paper came back and said, well, they didn't like the fact that it was done manually, that a person had actually flipped coins, because that allowed the problem that you could introduce error or bias. And so it's better to have your computer virtually flip coins. And this is what I just described is exactly the computer flipping a coin virtually. So it's very useful for things like randomizing patients. Now, all probability distributions have two features to them that are very important. They have a mean and a variance. And this mean and variance are just like the mean and variance that we talked about in the first week of the course. So in the next couple of modules, I'm going to tell you how to calculate the mean and variance for a probability distribution rather than for data. And we've already seen some mean and variance of probability distributions. We saw the normal curve before. The normal curve has a mean and it has a standard deviation. So we've seen these before. Now I'm going to show you how to calculate them.